galvanometer, right? We discussed about what is ammeter and what is voltmeter, and we discussed how to convert galvanometer into voltmeter and galvanometer into ammeter. So let us quickly revise those. So a ammeter is a device used to measure the current, and a galvanometer is already a device used to measure the very small current, or it is also used to measure the direction, that means to indicate the direction of current flow in the given circuit, right? So that is use of the galvanometer, but it is a very sensitive device, that means it measures only a small current there. And so now in case of to increase that means the range of this galvanometer, that is nothing but we discussed it as conversion of galvanometer into voltmeter, right? Ammeter, conversion of galvanometer into ammeter. So to convert that, we connected a small resistance called shunt resistance across that galvanometer, that means in parallel with the galvanometer. So if we connect like that, then it converts into the ammeter, that means it can measure the large currents now. And similarly, and to convert the galvanometer into voltmeter, we should connect a high resistance in series with the galvanometer. So that is the conversion. High resistance must be connected in series with the galvanometer. So right. So it is a conversion process there. Conversion of this galvanometer into voltmeter and conversion of this galvanometer into ammeter. Right. So this is like. For this conversion of galvanometer into ammeter, we need to connect a small resistance in parallel that we call shunt resistance, and to convert this galvanometer into voltmeter, we need to connect a high resistance in series with this. So that is a conversion, and we discussed some basic problems based on that also. So right, now let us see some more problems based on this conversions here, conversion of galvanometer into voltmeter and ammeter. And so now let us see this. A galvanometer having that resistance 30 ohms, 30 divisions, galvanometer having 30 divisions has a current sensitivity of 20 microamperes per division, and it has a resistance of 25 ohms. How you will convert this into an ammeter measuring up to 1 ampere? How you will convert this into voltmeter measuring up to 1 volt, right? And so now here the current sensitivity is given. So for this problem, generally you know to calculate this, we need to calculate first IZ value. So that means remaining this, this is the galvanometer resistance here. This 25 ohms is the resistance of the galvanometer G, and this is the I value. If you want to convert this into ammeter, this is the I value range of this ammeter. So then to apply this shunt resistance formula, we need IG value. So IG value is not directly given here. So but here the given is 30 divisions it has, and its current sensitivity is given as 20 microamperes per division, and so that then we can write this as IG value. That means IG value we can write this as simply the number of divisions into the number of divisions are 30. So 30 into current per each division. So that is 20 microamperes. So 20 into 10 power minus 6. So that gives us 6 into 10 power minus 4 amperes we can write. So that is the IG value now. That means for one division the current is given here. The given information here is it has 30 divisions, and for one division it reads this 20 microamperes here. And so then for the 20 microamperes per division means to turn from 0 to 1 division, it requires a 20 microamperes here. That means now we need to suppose here maximum 30 divisions are there. So if it goes to 30 divisions, then current is nothing but 30 into that 20 microamperes. So that gives us 6 into 10 power minus 4. Now from this we need to calculate this shunt resistance values there. We know already this formula here. The shunt resistance is nothing but it is given by like G by I by Ig minus 1. So then just you need to substitute those values here. G is 25 ohms and I value is 1 by this is 6 into 10 power minus 4 minus 1. And then simplify this, then you will get this shunt resistance value here. So right. So this is nothing but you can write this as 25 by 10 power 4 by 6 minus 1. And so then simplify this shunt resistance, then we are getting this shunt resistance value as, if we simplify that, 0.015 ohm. So this is that is a shunt resistance value there. So then And here that is a way of solving this shunt resistance here. Then when this number of divisions and current per division is given here. And similarly the same process for this voltmeter, finding this range of this that means resistance to convert the voltmeter on. So here I should mention that in options they will give that this much of resistance connected in series and connected in parallel. Both the options will be there. So you need to remember that point also. This 0.015 ohm must be connected in parallel with the galvanometer to convert that into ammeter, right? And whereas to convert that galvanometer into voltmeter, we know this is our formula for this, and from this we write directly this R value as we know this formula here, R is equal to V by Ig minus G. So this we can write here. Then this is nothing but V value is now 1. So we need to measure up to 1 volt here. So that is the range of this voltmeter. By Ig means we mentioned there, that is 6 into 10 power minus 4 minus this G value is 25. And so that gives us a resistance here. So that resistance is nothing but we can write this value as 0.985 ohm. So that is the resistance of this high resistance. This much of resistance must be connected in parallel in series with this galvanometer there. So then this is the resistance required. And so then this resistance must be connected in series with that galvanometer so that it converts into the ammeter there, right? Next, say this one here. So such a type of problems you can solve them easily. Direct formula based problems will be there. Sometimes instead of giving that IC value, they will give the number of divisions and the current per division they will give. So then you can convert that into IC value, full scale deflection current. So IC is called maximum current that can flow through the galvanometer, and which is also called as full scale deflection current. In most of the problems they will give that value as full scale deflection current only. So full scale deflection current means IC value. And so now let us see this problem here. A voltmeter of resistance RV and ammeter of resistance RA are connected in series across a battery of EMF E and of negligible internal resistance. So when a resistance R is connected in parallel with the voltmeter, the reading of ammeter increases to 3 times while that of voltmeter reduces to 1/3. Calculate the RA and RV values in terms of R. So now here these are now voltmeter, ammeter and voltmeter here. Now these two are connected in series. Here in this problem they are connecting in series here, but in generally we know how to connect them. So voltmeter is connected in parallel and ammeter is connected in series, right? So but here in this problem they are giving the data like this. Ammeter is connected, ammeter having this resistance RA and voltmeter having this resistance RV, both are connected in series. And now with this cell of EMF E, and the given information is when this resistance R is connected, now that there will be changes in the values of readings of the ammeter and readings of voltmeter. So from that we need to find this RA and RV values we need to find here. So let us see here, just we are taking this I is a current flowing through this. Then we can write this as simply, that is a simple equation only. So simply they are writing this E is equal to I of R plus RA plus RV, because initially only these two resistors are there now. So that means initially we are taking this current as I, and so that you can write this equation here. That means there what we are writing is that I is equal to, we can write this as, or E is equal to I into total resistance we are writing. The total resistance is nothing but RA plus RV we can write here, or from which we can write this I is equal to total EMF as E and total resistance is nothing but RA plus RV we can write. And now here when you are connecting this resistance here, when this resistance R is connected in parallel with the voltmeter, so then we are connecting in parallel with this voltmeter here. So in parallel to this voltmeter, now we are connecting a resistance now. So in parallel to this we are connecting a resistance R. So then the reading of ammeter will become 3 times. That is a given information here. The reading of ammeter increases to 3 times while the reading of this voltmeter reduces to 1/3. And so now the reading of ammeter means initially now we consider the current as 1 I. Now it becomes 3I. So that is the current, now we are taking it as 3I. when I is flowing through this galvanometer, then potential difference across this is IR, for example. Now the given information is the reading of this voltmeter is decreasing to 1/3, and so the reading of this voltmeter, the new reading of this voltmeter must be equal to IR by 3, right? IR V, this is resistance of the voltmeter, because initially it is IR, it is decreasing to 1/3 here, so that this is IR by 3. That means from this what we can conclude is the current flowing through the voltmeter is initially I, but now it is decreasing to I by 3. So current passing through this voltmeter, now we can take this as I by 3. And so then remaining current will flow through this resistance here. So remaining current is nothing but this total current is 3I. Then now we are writing the current through this resistance here, external resistance connected there. And so now here this is, this is 3I minus I by 3. Got it? Because here total current 3I is coming from this battery here, 3I. Now out of this 3I, this I by 3 is flowing to this. I by 3, how we are concluding means, because the reading of this voltmeter should decrease by 3 times here, and so that IR by 3, so current should decrease by 3 times. So the remaining current must pass through this. And so now this remaining current is nothing but I can write this as 8I by 3. Now this resistance and this voltmeter both are in parallel. So potential difference across them must be same. So then from that what we can write is the potential difference across the voltmeter must be equal to potential difference across that resistance connected in parallel with this. And so potential difference across this voltmeter we can write as I by 3 into RV. This is the potential difference across the voltmeter. Now the resistance across that resistance is nothing but IR. Now it is I by 3 into R. This is the resistance value here. And so now from this we can write this reading of this, that means the resistance of this voltmeter we can write this as 8R. So this is the resistance of this voltmeter. Got it? So just here we are taking how the changes are taking place. Initially we are taking as current as I. Now according to the given information, current should become 3I. And now the reading of this voltmeter is initially IR. That means I into RV. Now it should decrease by IR by 3. So that means current passing through the voltmeter should be decreased to I by 3. The remaining current should flow through this resistance connected only. So just we are equating the potential difference across them. So then that is the resistance of this voltmeter. And next we need to find the resistance of this ammeter also. So that is also our question now. So resistance of this ammeter we need to find here. For finding that resistance of ammeter, just we are applying the Kirchhoff law along this loop here, the horizontal circuit. If you apply along that horizontal circuit, then what we can write is, suppose I am applying along this direction here. So we are traveling in the direction of current. Here resistance is there. So we are traveling in the direction of current. So minus 3I into RA. And across this resistance of this voltmeter, there the current is only I by 3 into RV plus E. This is equal to 0. And therefore from this we can write this E is equal to like 3IRA plus IRV by 3 we can write. Got it? Just we are writing this, applying the Kirchhoff law here. And so now from this we can write this equation as this E value. For E value already we mentioned one expression here. So this is another original expression for this E. And so now we can equate with this. So now just if I equate with that, this value we can write it as IRA plus IRV. So this is equal to 3IRA plus IRV by 3. And just we can simplify this. By simplifying this we can find this relation as like 2RV by 3 is equal to 2RA. I will be cancelled. So then this is the relation what we are getting here. Or from this RA is equal to, we can write this as RV by 3. This 2 also we can cancel here, right? Now this RV value we already calculated here. This RV value is nothing but we got this value as 8R. So then you can substitute this as 8R. And so therefore this RA is equal to 8R by 3. So this is the resistance of this ammeter in terms of the resistance connected there. So like that we can solve this problem easily. And whereas if you are solving by taking any other equations, it will be simply lengthy equations you will get if you are taking like I1, I2. So simply here I am taking this initial current as I and final current directly I am taking it as a 3I, so that you can solve this problem easily, right? And so next here let us see. So then generally I said whenever you are connecting the resistance in parallel with that galvanometer, the range of the galvanometer will increase, but the sensitivity of the galvanometer decreases. So when you are connecting any resistance there, so sensitivity decrease means generally we can say that suppose in the galvanometer initially suppose say this needle is suppose 0 here. Now for one division it reads 1 microampere for example initially when it is in the like a galvanometer, given galvanometer. Now we are increasing the range such that it measures this the same one division will measures the 10 microamperes, or let us say 10 milliamperes, 10 microamperes or 10 milliamperes, like this. We are increasing the range. So that means now the same, for the same deflection it is measuring more current here. Now our current sensitivity is nothing but theta by I. Current per unit, deflection per unit current is nothing but equal to current sensitivity. So the theta value will remain same, this deflection will remain same, but the current value is increasing. Initially it is only this 1 microampere, now it is say 10 milliampere. So this value is decreasing here, current sensitivity will decrease, right? So you are increasing the range of the galvanometer means we are decreasing the sensitivity of the galvanometer. So that means now see this question here. Is a shunt of resistance 1 by N and value of galvanometer resistance, sorry, the shunt of resistance 1 by N, 1 by N the value of the galvanometer resistance is connected in parallel with the galvanometer. How will the current sensitivity of the galvanometer changes? That means now the shunt resistance value they are giving here. The shunt resistance value, how much we are connecting means we are connecting this shunt resistance as 1 by nth of resistance of the galvanometer here. The resistance of galvanometer is G. So then G by N we can say here. So that much of resistance we are connecting here. And so now let us say this problem here. We know already we defined the current sensitivity in the beginning itself. So current sensitivity is nothing but deflection per unit current. And this figure of merit is a reciprocal of that. I by E is nothing but reciprocal of current sensitivity, that is deflection per current per deflection here, figure of merit means, right? And so next here the deflection initially suppose we are taking as theta dash in the given galvanometer. In the given galvanometer we are taking this deflection as theta. Now we are connecting this shunt resistance so that this deflection of this galvanometer, that means will changes to some theta dash, right? And so now see this, the deflection of the galvanometer is proportional to the current passing through that. We already discussed it there. That means now the current passing through this galvanometer is nothing but I. Potential difference across that is VIG we can write. When more current is passing here, then here it shows a more deflection here. And in detail the mathematical equation we will discuss that later. In electromagnetism you will get the working of the galvanometer. So in that we will get the mathematical relation of this theta by I and how it depends on this theta values there. So simply here what we can say is, when more current is passing here, then it shows a more deflection here, right? That we know already. If it is more current is passing here, then deflection of this galvanometer will increase. That means theta value will increase. So if I value is increasing here, then theta value also increases here, right? The deflection of this galvanometer also increases. And so then we can say that these two are proportional. Theta and I are proportional. So that they are writing like theta dash by theta is equal to Ig by I. So Ig by I, just we are writing the ratio here. So here this is the theta dash here, the theta dash and current flowing through this is Ig. Now here initially it is theta, now the current flowing it is I. So then it is theta dash by theta is equal to I by Ig we are taking here. Theta dash and theta are the deflections of the shunted galvanometer and simple galvanometer. So this is the theta dash is the galvanometer, that means deflection of the shunted galvanometer, and theta is the galvanometer, simple galvanometer deflection here. And so now here now current sensitivity, now we can write this as theta dash by I. So theta dash and I is the actual current entering the circuit here. Now we know this total arrangement will behave like a ammeter. This total shunt resistance plus this galvanometer will behave like a ammeter. Now the current measured by this ammeter is nothing but I, right? And so now here that current sensitivity after shunting we are writing here. After shunting this current sensitivity is theta dash by I we are writing here. Theta dash by I. And so now this value we can write this as Ig by I into theta we are writing here by using this relation. Theta dash value just we are substituting here from this. So that means from this relation you can write this theta dash is equal to, I can write this theta dash as theta into Ig by I, right? So that value we are substituting here, that theta dash value we are substituting here, and so that now you will get Ig by I into, like suppose if I substitute there, the new current sensitivity is nothing but, so 1 by I into that theta dash value we are substituting as Ig by I into theta we are substituting here, right? And so now this value we can write it as Ig by I into this original current sensitivity we can write here. The original current sensitivity is nothing but that value theta by I. That is the original current sensitivity when you are taking a pure galvanometer without any shunt. And so now this relation we can write this as for the shunted galvanometer, that S is nothing but S by G by N. That is a given information. Now from this we are finding the relation between I and Ig values. So we know that for this galvanometer here, suppose a galvanometer is there and here this shunt resistance is connected here. The current flowing through this galvanometer is Ig and current flowing through the shunt is I minus Ig. And since both are connected in parallel, just we are equating the potential difference there. So that means now Ig into G must be equal to I minus Ig into S. Now that S value is given as G by N, right? So just we are using that relation here. So then by simplifying this, you will get this Ig is equal to, we can write this value as I by 1 plus N. So this is the Ig value here. And from this we can write this expression as Ig by I is equal to, Ig by I is equal to 1 by 1 plus N we can write. Now this Ig by I is nothing but our relation here. Therefore this new current sensitivity is nothing but, so this is the relation here. The new current sensitivity is nothing but, we can write this value as Cs dash is equal to Ig by I into Cs. This is the relation found in the previous slide here. In the previous slide, now that means here we got the relation here. Now Ig by I value we calculated from this, and so that this Cs dash is equal to Cs by 1 plus N we can say here. So that means whenever you are shunting the galvanometer, that means shunting is nothing but we are connecting a small resistance in parallel here. The sensitivity of the galvanometer will decrease. And so if resistance of the shunt is 1 by N type galvanometer resistance, then this is the relation between the sensitivity of galvanometer before shunting and after shunting, right? So that is simply if they ask any theoretical question how the sensitivity changes, means if you are increasing the range of the galvanometer, current sensitivity decreases. By the definition itself you can say that point there, as I said previously, right? And so now let us see the another important type of important models regarding this. Now see this, a candidate connects this moving coil galvanometer. Moving coil galvanometer is nothing but simply galvanometer only. That is nothing but what we are using here. The coil will deflect there, so that it is called moving coil galvanometer. It's, as I said, its working we'll discuss later. A moving coil ammeter A and resistance R are connected in as shown in figure. If the reading of if the voltmeter reads 20 volts and ammeter reads 4, then R value is. So then R value now we need to identify here, right? This ammeter reading and voltmeter readings were given here. From this we can write this R value. If for example all are ideal, if all the devices are ideal, then what we can say is V is equal to IR formula we can apply there, or from this we can write R is equal to V by I we can write here. So which is nothing but like 20 by 4 you can say it as a 5 ohms, right? If all are ideal, but not here the case. So here the case they are giving that they are moving coil galvanometers. Moving coil galvanometers means they are practical voltmeter and practical ammeter here. They are moving coil devices means. So that is definitely they possess some resistance here, right? So definitely they possess some resistance. So that means these are not ideal. If they possess resistance, then what will happen? We know that if this possess, actually it should possess infinite resistance, so that no current will flow through this path here. Total current should flow through this resistance only, right? But if it is having some finite resistance, then some current will flow through this voltmeter, and some current flowing through the resistance now will be less here. Suppose now I am taking this, some current is flowing like this. So then some current I am taking, like I is flowing along this direction here. Out of this 4 amperes, here 4 amperes current is entering here. So out of this 4 amperes, some I current is flowing along this path here, right? Then the current flowing through this resistance will become 4 minus I amperes, right? So this is the current flowing through that resistance. Now the potential difference across this must be the reading of this voltmeter. And so now from this what we can write is this V is equal to R into 4 minus I, right? And therefore this R is equal to V by this V by 4 minus I we can write here. So this value is nothing but V by 4 minus I. That V value is nothing but the reading of voltmeter is given there. So the reading of voltmeter is 20. So 20 by 4 minus I. Now from this you can say whether it is equal to 5 or less than 5 or greater than 5. So definitely practical voltmeter means this I value is non-zero. This I value is non-zero means some current definitely will enter into that voltmeter. So then this value will be less than 4 you will get. If this value is less than 4, then you can conclude that this value must be greater than 5 ohms here, right? So that is the resistance possible there. Got it? So the now the resistance, if you are measuring this, if you are neglecting that, you will get 5 ohms only, but actually the resistance will be greater than the 5 ohms you will get here, because a part of current will flow through the voltmeter. So current passing through this voltmeter is not 4 amperes, so only 4 minus I will pass through this resistance there. So when 4 minus I is passing, then potential difference across that is 20 ohms. So then 20 by 4 minus I means you will get this value as greater than 5 ohms you will get. So that is the value of this resistance. It is not equal to 5, you will get greater than 5. And based on this, some more problems will be there. Let us see here what will happen when you are connecting the resistance, that means voltmeter like this, and when you are connecting this, another arrangement is like this, ammeter and resistance, and across this we are connecting this voltmeter, and here across the only resistance we are connecting the voltmeter, right? And so now let us see this type of problems now. And so now see this data here. To measure the resistance, of R, a resistor, R of a resistor, a voltmeter of resistance RV is placed across the resistor, and an ammeter is placed in series with this combination as shown in the figure. Find the resistance R in terms of the measured readings of this ammeter, I means, and the reading voltmeter, I means. That means I measured value here. And so now discuss the result if for RV very much greater than that of I measured by V measured by I measured. So that means now these are the measured values are given here. So in terms of that measured values, we need to find this resistance here. So which we discussed now previously. This problem is now same as that of our previous discussion here. This numerical expression. And so now let us see here the potential difference across this resistance. Now we are taking this as some I1 is a current flowing through this voltmeter. Now we are taking here the reading of this ammeter is nothing but I measured we are taking here. So out of this I measured, some current is flowing through this voltmeter and some current is flowing through this resistance here, like similar to that of our previous problem, right? And so now here this I1 we are assuming here I1 is the current flowing through this voltmeter. Now here this value is I means minus I measured minus I1 we are writing here, and so now just we are equating the potential difference similar to that of our previous. So the potential difference here means we can write this as I1 into R. So here that equation is I1 into R RV is equal to I measured minus I1 into R, that resistance, and this is nothing but they are giving this value as I mean. That means V measured. This value is nothing but V measured. So you can equate this value as V measured is equal to R into I measured minus I1 we can write here. This is nothing but our V measured value here, right? And so now this is nothing but the equation here. So this equation what we are writing is this equation only. I measured minus I1 into R is equal to I measured. But now this I1 value we can write it as, see this, from this relation, if only this term if you are considering here. So from this relation we can write this as I1 is equal to V measured by resistance of this voltmeter we can write. So that is nothing but what we are substituting here. This I1 we are replacing as V measured by RV we are resistance of this voltmeter we are writing here. And from this we are writing this R is equal to the resistance value. The numerical value of this resistance is equal to R is equal to V means by I by I means minus, that means I measured minus V measured by RV. Just we are writing this term in denominator. So this is the expression for this, right? And so now here they are giving this, the first problem here which we discussed already. This is nothing but our previous problem. Here we are writing in terms of numericals there. They are giving some other values here. So here just we are replacing this I value in this problem as, if V is a measured value there, like we are replacing this problem as 20 by 4 minus this I value we can write it as 20 by resistance of this voltmeter we can write here. So like this we are writing here now in this problem. Got it? And next here another condition is given here. So let us see this condition. Now we need to answer the same question. When this resistance of this voltmeter is very much greater than that of this value here, that means this resistance is it is having very high resistance there. The resistance of this voltmeter is very much greater. And so now we are writing like 1 by R is equal to, I by R is equal to, we can measure like I measured by V measured minus 1 by RV we are writing here. Just we are writing like effective resistance meaning there. Like this effective resistance is nothing but we can write this effective resistance as effective resistance of this combination. So here voltmeter and this resistance are in parallel. So that this 1 by R effective we can write this as 1 by R effective, that is nothing but I measured by V measured is equal. Now this is nothing but our 1 by R effective resistance there. So this is equal to 1 by R plus 1 by RV. Got it? This value is nothing but what we are writing here is I by R by, that means this effective resistance, both are in parallel, so that effective resistance we can write as 1 by R plus 1 by RV. So that is nothing but our 1 by R effective. Now this 1 by R effective value we can write it as, from this data, just if potential difference and resistance or potential difference and current are known to us, then resistance we can calculate like this. So by using that given data, effective resistance we can calculate like this. And so now here the given information is, so in this relation just we are writing this as, we are writing like 1 by R is equal to, so 1 by R is equal to what we are writing is I measured my V measured minus 1 by RV we can write here. Now the given information is this value, this is the given information here, or let us say here it is explained here. So then this RV value, given value is RV value is very much greater than that of V measured by I measured. Now 1 by RV is very much less than that of I measured by V measured. So that means here this 1 by RV value is very much less than, just we are reversing this fraction here, very much less than this I measured by V measured. And so that we can write this value as, so that means now this value is negligible. So that we can neglect this 1 by RV value. So when that value is negligible, then we can write that resistance as V measured by I measured we can write here. So that means we can write that value as V measured by I measured we can write there. So that R is equal to V measured by I measured we can write here. That means if the resistance is, if the voltmeter is having very much high resistance, then we can write, you can directly write this as potential difference by this value we can write it as resistance of this, that required resistance there. It is having high resistance in the sense it is nothing but it is like ideal voltmeter there, right? So that is the case there, if it is resistance of the voltmeter is very high. And so next let us see this combination here. So now let us see this problem. So now the difference you should observe here in the previous circuit and this circuit. In the previous circuit, this ammeter is outside. Only these two are in parallel and ammeter is outside. Now this voltmeter, now in this problem, voltmeter is connected across the combination of these two. That means now in this problem, these two are in series. This resistance of ammeter and this resistance are in series. Now across this, this voltmeter is connected here. So now see this. To measure the resistance RA of the resistor, an ammeter of resistance RA and placed in series with the resistor, and a voltmeter is placed across the series combination as shown in the figure. Find the resistance R in terms of the measured readings of the ammeter I measured and voltmeter V measured, and discuss the result if V by R measured is very much greater than that of RA. So that means V measured by I measured is very much greater than that of this RA. So that is the given information there. That means now in this we are measuring this resistance like this. And so now again the same procedure we need to write here. This we are considering that I is the total current here. Out of this ammeter will measure the only current flowing in this path here. And so now this is I measured, and the remaining current I minus I measured is flowing to this voltmeter. That means across this path here. So that now the potential difference across this we can write this as I minus I measured into RV. And that should be equal to the potential difference across this series combination here. So here the potential difference we can write this as I measured into RA, total resistance, RA plus R we need to write. And from this we can write this RA plus R is equal to, by using these two terms we are writing here, first term and last term we are taking here. So then RA plus R is equal to V measured by I measured we can write here. And from this we are writing this as R is equal to V measured by R measured minus RA we can write here. So this just we are writing this RA term this side. So this is the resistance there. This is the resistance of required resistance there. If you know the resistance of the ammeter and voltmeter reading and ammeter readings are known to us, then we can calculate the resistance like this. And now let us see what will happen when this condition is satisfied here. So when this condition is satisfied, then you can say this relation as so from this relation we can write here. From this relation we can mention this as when this V measured by I measured is very much greater than that of this RA value. RA very much greater than that of RA means that is nothing but the resistance of this ammeter is very small, negligible. The resistance of this ammeter is negligible. So which is our required condition. So that means if the resistance of ammeter is negligible, then we can treat that as an ideal. Then it gives the accurate values. Then we can write this, if zero resistance is there, then potential difference across voltmeter and this resistance must be equal here. If the resistance of this voltmeter is zero, then we can write this resistance. That means now from this equation we can conclude that we are neglecting this value because this value is very small when compared to this V measured by I measured. So that this resistance R is equal to V measured by I measured. So that is the resistance there. When resistance of this ammeter is very small, we can neglect this resistance of the ammeter here, right? And so that is the type of problems there. And now let us see this other type of problems here, how to solve this different ranges of this galvanometer. Now see this problem. A galvanometer has an internal resistance of 50 ohms and a current required for the full scale deflection is 1 milliampere. Find the resistance in series required as shown in the figure to use it as a voltmeter with the different ranges as indicated. That means for the same galvanometer we can use it for the different ranges we can use here. And so then for this, if you are connecting between this terminal and this terminal, that means it measures the 1 volt only, maximum voltage it can measure is 1 volt only. If you are connecting between this and this terminal, then it measures maximum 10 volts, 0 to 10 volts. If you are connecting between this and this, it measures 100 volts. That means in the same galvanometer we can fix these different ranges like this by this arrangement here. So now they are asking how much this R1, R2, R3 are connected here. So that means now here this is R1. I think here printing is not clear. I am writing here this is R1 and this is R2 and this resistance is R3 here. And so now just to see this, first we know this IZ value, IZ calculation. From this let us write this R1 value here. Just this is our voltmeter conversion only. We know for this voltmeter conversion the resistance we can calculate by using this equation V by Ig minus G, right? and just this different ranges will be there, just you need to substitute those ranges itself. And so now for the first one, if I consider here, V means 1 by Ig value is 1 milli, that means 10 power minus 3 minus this 50. This resistance is 50 ohms here, resistance of the galvanometer. And so then this is nothing but 950 ohms you will get. So that means this value must be 950 ohms. So that means for the 1 volt, the resistance to be connected here is 950. Got it? Now let us go to the next range, 0 to 10 volts. Now 0 to 10 volts means the same formula we need to apply here. But now the resistance of this galvanometer means we need to consider this as R1 plus R2 we need to, G plus R1 we need to consider here. Right? G plus R1. That means the same formula we need to apply here. For this if we consider, actually what we need to write is V is equal to, where V is the potential difference across these two terminals if I consider here. Ig into, now what is the total resistance from here to here? G plus R1 plus R2. And so from this we need to write an expression for this R2. That R2 value now we can write this as V by Ig minus of G plus R1. So just this value, initially only G is there. Now G plus R we need to take it as a resistance here. And now we can substitute those values now. This is again 10 by this is 10 power minus 3 minus this 950, R1 is 950 we calculated already, and this G value is 50, so that you will get this as 1000. And so then it is 9000 you will get here, 9000 ohms, right? So that is R2 value. So like that. And similarly R3, if you are taking from here to here, the range of this voltmeter is then 100. So now let us see this. Here it is mentioned here the calculation. So then now for this 100 volts, Ig value they are writing. Ig is equal to V by total resistance. V by total resistance we need to write here like this by using this equation. Ig is equal to V by G plus R1 plus R2. Now we are including this R3 also. And again from this G plus R1 plus R2 plus R3 they are writing. And from this R3 is equal to, then this value 100 into 10 power 3 minus G plus R1 plus R2. Now these values R1 plus R2 values we already calculated, just you need to substitute those values here. And from that you will get this R3 value as 90 kilo ohms here. So that means to convert it into a voltmeter of this range, 100 volts range, so we need to connect this as 90 kilo ohm resistor. So right, so those are the R1, R2, R3 values there. And next such a similar problem is that this is the conversion from galvanometer into voltmeter of different ranges. Now let us see similarly when it is, if you are converting the galvanometer into ammeter of different ranges. So galvanometer shown in the figure has a resistance 50 ohms and a current required for the full scale deflection is 1 milliampere. Find the resistance R1, R2, R3 are required to convert it into an ammeter having the ranges as indicated. So that means now this range is 10 amperes. And this range is 1 ampere and this range is 0.1 ampere, right? So these are the resistors R1, R2, R3. So now here, for example, for the range 0.1 ohm if I consider here, 0.1 ohm, that means now A and Z we need to connect here. When you are connecting this A and Z, all these three resistors will be in series. Like between these two terminals we are connecting here. This terminal if you are taking 0.1, this terminal if you are taking, then all these three resistors will be in series, like current is entering the device like this and it comes out here. And so now these three resistors will be in series and that will be in parallel with this galvanometer. And so now out of this total current I here, then we can say that, and here it is explained it clearly only, so I will explain here. So out of this current I here, then Ig is the current flowing through this galvanometer, and then this I minus Ig is flowing here in this part here. And therefore now again we need to equate the potential difference. So potential difference across the galvanometer will be Ig into G, and this is R1 plus R2 plus R3 into I minus Ig. So we are equating them, and from this you will get R1 plus R2 plus R3 is equal to, you can substitute those values here. Ig value is 10 power minus 3 and this G value is 50 and I minus Ig value. I value is nothing but now the range of this ammeter is 0.1. So 0.1 you can substitute, then we are getting like 50 by 99. and this is for the range of 1 ohm. If you are taking the range of 1 ohm, now for the range of 1 ohm, we need to connect these connections between current enters at point A and leaves at the point Y, right? So like this. And so now we can say that only these two resistors will be in series, and now this R3 and galvanometer are in series. So R3 and galvanometer combination will be in parallel with this R1 R2. So now let us see this connection for this. R1 R2 will be in parallel with this G plus R. So again we need to equate the potential difference across this R1 plus R2 must be equal to potential difference across G plus R3. So now let us equate them. So then Ig into G plus R3 is equal to, now current flowing through this is again I minus Ig we need to consider. I minus Ig into R1 plus R2 we need to write. Now here I means we need to take 1. In the previous I means we consider it as 0.1. Now here our range is 1 ampere here. So then 1 we need to consider here. We will substitute that later. And from that I am taking this Ig term common here. So then Ig of this I1 G of G plus R1 plus R2 plus R3 will get, that is equal to I into R1 plus R2 will get. Now we are substituting all the known values here. And so then this I into R1 plus R2 into G value we can substitute here, and then this from this we are getting this R1 plus R2 values here. R1 plus R2 value we can write this as, so that means here R1 plus G plus R1 plus R2 plus R3 value we calculated already by using the first equation here. So that's value we are substituting here, and 50 we know already. And so then Ig into Ig is 10 power 3 minus 3, and this is 50 plus R1 plus R2 plus R3 is from this equation 50 by 90 by this I, this range of this voltmeter, and from this you will get this R1 plus R2 value as 5 by 99 ohms. And next similarly we consider the range from 0 to 10 amperes. So then when you are taking from 0 to 10 amperes, now we can observe the circuit will be like this. The circuit is R1 is in parallel with the combination. That means now this R2, R3, G are in series. These three resistors are in series. That combination is in parallel with this R1. So then again we need to write the potential difference across the combination of these three must be equal to the potential difference across R1. And our range of ammeter is now 10 amperes. And so now here again we are equating the potential difference here. The potential difference across this combination is Ig into G plus R2 plus R3, because these two are in series with the galvanometer. That should be equal to Ig, I minus Ig into R1, the potential difference across this. And again from this we are finding this R1 value here. If we find this R1 value, then we can write this as Ig into G plus R1 plus R2 plus R3 by I. Now again we can substitute this G plus R1 plus R2 plus R3 value by using our first equation. That means this G value is 50, R1 plus R2 plus R3 is 50 by 99, and Ig value is 10 power minus 3. Now in this problem I is 10 ohms, 10 amperes. So that means 10 amperes we are substituting here. From this you will get this R1 value, and then by using this R1 value we can substitute in our second equation. Here the second equation we are like this equation we are getting like R1 plus R2 is equal to 5 by 99. So here we are substituting this R1 value. From this you will get R2 value. Then now this R1 and R2 values we can substitute in this equation here. Here one more relation is there. R1 plus R2 plus R3 is equal to 50 by 9. So by substituting an R1 R2 values you will get these values like this. So that means R1 value is 1 by 99 and R2 value is 1 by 22 and R3 value is 15 by 33. So those are the resistance to be connected there. So those are the some important models based on the conversion of the galvanometers into ammeter and voltmeters there, right? And so now solve all the problems based on this, and this part is important for this examination, advanced or mains examination, as I said many times. So practice the problems thoroughly, and again we will discuss working of the galvanometer and how the current is proportional to theta. We will derive all those expressions and we will discuss that expressions in the electromagnetism. And again there also some problems will be there based on these conversions, and there also we discuss this topic again. So if you understand here just conversions here, then it will be easy there. Just we are discussing here conversion of galvanometer into voltmeter and ammeter, and in that electromagnetism we will discuss how that galvanometer works. So right, so then practice the problems based on this. In the next class we will discuss about the remaining meters like meter, bits and potentiometer. Right, thank you. Practice all the problems based on this.